All right, everyone, we are back and we're going to do our Pset 3 solution video. So let's look at some defects. We've got a vacancy here. We have got a self-interstitial here. These are all 0D, 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 0D. This is 1D, this is 2D, this is 3D. And Frankel and Schottky pairs there are all 0D defects. And we need that cation, anion lattice in order to do that. This would be a substitutional impurity, as would this, and this would be an impurity interstitial. And I don't see any grain boundaries or edge dislocations or voids here as well. Excellent. So Schottky and Frankel defects for Ti2O5. So we're going to go null goes to vacancy in Ti minus 1, 2, 3, 4, 5 plus a vacancy in oxygen, which is going to be 1, 2. Put the 5 there, put the 2 here. Good to go. The Frankel defects for cation, which is Ti, is going to be vacancy of Ti, 1, 2, 3, 4, 5, plus Ti interstitial, 1, 2, 3, 4, 5. Same thing for oxygen, vacancy in oxygen, 1, 2, plus oxygen interstitial, minus 2. Oops, forget that one there. Excellent. Which reaction dominates? We have this general expression for the concentration of vacancies or defects, scales exponentially, minus delta HF over KT. So lower enthalpy of formation, higher concentration of defects. That is going to be our Schottky defect. Great. Write 3 defect reactions for the incorporation of this into this, meaning Ti2O5 is going to be our impurity, and our host atom is going to be Fe2O3. So we're going to do, I'm going to go backwards, substitutional cation first. So Ti into Fe, 3 plus to 5 plus, so I need a gain 2, plus... I'm going to jump, actually, I'm going to do a vacancy of Fe, which is going to be minus 3. Now, I need at least, I have this kind of stoichiometry issue. So I need to balance, I could just put a 3, but if I do that, then I'm in trouble here. Or I'm in trouble because I need this to be intervals of 2. So what we can think about, what if I put, how about 6 and 4? How about that? 4 times 3 is 12, 6 there. So then that would put a 3 here. I'd have 10 total here, so I could put a 5 here. So that looks good. Plus oxygen, oxygen, X. And how many? 15, 15. There we go. Great. This one's done. Cation interstitial. So let's try to do something different. Fe2O3. So cation interstitial, a substitutional cation, so Ti interstitial goes to 1, 2, 3, 4, 5. I'm going to pop a 2 here just because I want to keep it right there as well. So I need plus a vacancy. Now, this is where we get a little bit tricky because minus 3. So we might have to change that. So how about this? Fe minus 3 again. We can't really... Let's see how we're going to have to match that one. So I need to get this to an even. So I can go 10. That'd be 30. So this had to be 6. That's fine. That's fine. And then, yeah, same stoichiometry there. 15, oxygen, oxygen, X. Great. And then finally, Ti2O5, Fe2O3. Once you hit that stoichiometry, that factored in, you're going to be good to go. Anion vacancy, so I'm going to do vacancy in the anion, which is going to be positive here, plus, why don't I can do now, how about a Ti interstitial, 1, 2, 3, 4, 5. I'm going to do 2 of them, because I need to hit that ratio. So now I've got 12, 10, 12. So now I'm going to do a vacancy of Fe, and then I'm going to do minus 3, and I'm going to do 4. 4 times 3 will give me 12. So I need 2 here. And then minus 12. Good. So now let's do mass balance Ti2. Good. O5. So I need plus oxygen, oxygen, X. I need 4 more. I need 5, actually. Excuse me. I need 5 of this. So 5 oxygens here. And then that'll give me 6 on this side. We're good to go. Great. Let's do it again. Except now, incorporation of KCl into AlCl3. So let's go vacancy, anion vacancy. So vacancy in the anion, which will be Cl, which will be a positive one. So vacancy in Cl plus, now let's go ahead and let's figure it out. If I do, how about we do this? Let's do plus a K interstitial. It's going to be also 1 plus vacancy in AL, which will be -3. And then, I mean, I could just put a 2 here. So we can balance this. We can put a 2 here. So now our +3, 2 KCl. Leave the rest. So Cl here, we have 1. So I need plus 2 ClClX. So that gives me 2 plus 1 here, 3 for Al, 1 Al, and we're good to go. All right, so we have the anion vacancy. We need a cation interstitial. We actually already satisfied that condition, but let's do a little bit more. Let's do cation interstitial 1, and I'm just going to do 3 plus vacancy Al minus 3 plus 3 ClClX. And then finally, KCl goes to AlCl3, KAl, Al is +3 to +1, so this will be -2. So now I need to do something a little bit fun. I could put 2K interstitial. That's good. So that balances. So I need 3 of these, and then plus 3 ClCl. There it is. That's it. Draw this burger circuit for all the planes below. If any, all of these are going to be 1D defects because they're either edge or screw. So this side is fine. This side is fine, although you should just still draw it anyways. I'm going to select my tangent vector coming out of the board here. So I'm going to go and I'm going to pick my starting point. I'm going to pick my start right here. So I'm going to curl right-hand rule. So I'm going to go 1, 2, 3. 1, 2. Actually, I'm going to do 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. So I'm curling around this, then 1, 2, 3, 4. Remember, it's start to finish. So my relationship here is Burger's vector is perpendicular to my tangent vector. That is a 1D defect, and that is an edge. Oops, edge defect. Here we're clear, here we're clear. I'm going to go up and basically pointing up here. I'm going to start right here. I'm going to curl around, and I'm going to go 1. I'm just going to go 1. And then I'm going to go 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. So I did 1 step here, so I need to go 2, 3, 4. Start to finish. Remember, that's our convention. Burger's vector is parallel to our tangent. That is a right-hand screw, also 1D defect. And that's it. That's our problem set 3. So we'll see you in the next video. Thanks. Bye.